Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the module 8 where we are going to study about the composition of the mantle and core. In the lecture 1 today, we will be discussing about density variations within the earth. More specifically, we will see the Adams-Williamson's equation, and then we will also be talking about the pressure variations within the earth. Finally, we will be having the summary of today's lecture. So, as far as the density within the earth is concerned, we can include density of the earth, and that can be combined with the velocities to derive elastic constants. And in order to find out the average density of the earth, we can first find the earth's mass, and that can be found out by using the law of gravitation. So, as per the law of gravitation, the acceleration due to gravity is equal to the gm by a square, where capital G is the gravitational constant, that's equal to 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. And acceleration due to gravity, we know it already, that is equal to 9.8 meter per second square, and the radius of the earth is 6371 kilometer. So using this, we can easily find out the mass of the earth, but we know that the volume integral of the mass gives the density, and the earth's density varies with depth as well. In order to find out the density, average density of the earth, you can divide the mass by its volume, and then finally whatever density you will get, that will be your average density, which will approximately be equal to 5.5 gram per centimeter cube. But this value that we just had is significantly higher than the density of the surface rocks. So if you compare the surface rocks density, that is approximately equal to 3 gram per centimeter cube, but we are getting our average density of the earth is around 5.5 gram per centimeter cube. That means the inner material of the earth is made up of a different kind of material which is much denser. So this particularly provides a first evidence for the core of much denser and different material. And second indication of the dense core comes from the moment of inertia about the rotation axis. If we are considering this is the spin axis of the earth, and we are taking any elemental volume over here, that is dv, and which is a perpendicular distance l away from the spin axis, then in terms of r, theta and phi, we can possibly write the value of the moment of inertia, that will be equal to m r square, that means rho dv, and the perpendicular distance l square, and that is the integral over r, theta and phi, and we can write this l square rho and r, theta, phi dv, and these values will vary from 0 to 2 pi, 0 to pi and 0 to a, and we will be having integral of density depending upon the value of r, and then L, that will be equal to r sine theta, so r square sine theta, sine square theta it will be, and then r square sine theta dr d theta d phi. When you will solve this entire integral for 0 to pi and 0 to pi, then it will become 8 by 3 pi 0 to a rho r to the power 4 dr, and then the moment of inertia to the mass gives a scalar that basically depends upon the density variation. So what we are going to do, we are basically take the ratio of the moment of inertia to the mass, and that will give us a particular value and that should be basically representative of the density variations within the spherical earth. So we can consider three cases. The case one will basically about the homogeneous earth, where the density will be uniform all across the globe. And in the second case, we will consider that the mass is at the surface of the earth. That means we are considering all the mass should be concentrated in a shell near to the surface of the earth. That will be the second case. In the third case, we will consider a more realistic case in a two shell planet, where the mantle density will be rho m and the core density will be rho c, and the core's radius will be rc. So let's look at the first case, where we are considering the earth as a homogeneous sphere, and the density everywhere would be equal to the average density of the earth. That means the density as a function of r will be rho naught everywhere. So if we incorporate these rho r as rho naught into this previous equation of moment of inertia c, then we will get c is equal to 8 by 15 pi a to the power 5 rho naught, and the mass, that we know mass is volume times density, that is 4 by 3 pi a cube rho naught. And the ratio, if we will calculate the ratio of the moment of inertia to the mass, then it will come equal to 0.4. Then let's look at the second case, where we are considering all the mass to be concentrated in a shell near to the surface, and we are going to consider the density as a function of r as a product of the density at the surface to the Kronecker delta function, and this Kronecker delta function will be equal to basically 1 when r is equal to a, and it will be 0 when r is not equal to a. So when you are considering r is equal to a, that means the entire density will be in a shell near to the surface. So that will basically be equal to density of the surface rho s. And when we do our calculations for moment of inertia for this particular case, then c will be equal to 8 by 3 pi a cube rho s, and the mass will be equal to 4 pi a square rho s, and the ratio of moment of inertia to the mass will become 0.67. That basically is a quite large value, and which but further means that a distribution with material concentrated towards the outside gives a larger ratio. So basically what you can see in here is that if the mass is concentrated toward the surface, that means you are getting the ratio to be larger for the moment of inertia to the mass. And if you are keeping the homogeneous sphere for the earth, where the density is equal at each and every point of the earth, then its ratio will be 0.4. That means you are basically reducing the ratio as soon as you are coming from the case second to the case first. And then the third case, that will be the more realistic case, where we are considering the entire earth as a two shell planet with a mantle density of rho in subscript m and a core density of rho in subscript c, and the radius of the core is rc. The integral we can evaluate for c, that will be 8 by 3. If you look at this integral over here, c is equal to 8 by 3 pi integral 0 to a rho r r4 dr. So it will be something like that. 8 by 3 pi will be basically common, and we will solve separately for the core and the mantle both. Then for the core, that is having the radius rc, then it will be basically, this should be rc. So 0 to rc rho c r4 dr plus integral, then for mantle from rc to a, that is the total radius of the earth, then rho m, that is the density of the mantle, multiplied to the r to the power 4 dr, then it will give this particular expression for the value of moment of inertia. Similarly, you can calculate the mass, that will be equal to 4 by 3 pi in bracket rho c minus rho m r cube c. And when we take the ratio after considering the values of rho m, rho c and rc similar to those of the earth, then we can take these values. Rho c is equal to 12 gram per centimeter cube, rho m is equal to 5 gram per centimeter cube, and radius of the core is 3480 kilometers. So finally, when we'll incorporate all these values to this particular expressions, this one and this one, then you will get the ratio of moment of inertia to the mass is equal to 0.35. So you can understand this. So in the case one, what we have taken the Earth to be uniform. The density at each of the place of the Earth is uniform, and in the case second, we considered that the earth is having entire mass near to the surface, somewhere over here near to the surface it is having, and all the mass and the density is distributed near to the surface, and we considered for the density of the earth in this case as a direct delta function r minus a into rho s. Rho s is the density of the surface. This was your case second. In case 3, what we have seen, we have considered a two shell planet where we have a core and there is a mantle. Core density is rho c and the rho m is the mantle's density, and the radius of the core we considered as rc, and the value of c upon ma square we got is 0.35. In this case, in the second case, we got value of c upon ma square as 0.67. In the uniform sphere case, we got the value of c upon ma square as equal to 0.4. So basically, when we are moving towards having more material towards the core, then its value is keep on decreasing. And if we compare these values with the realistic value of the earth that is found from the earth's shape and the gravity, that is basically equal to 0.33. So more realistic case was the case 3, where we considered the earth to be a two shell planet having core and the mantle, and the core's density, if we take the higher side, that is 12 gram per centimeter cube, and the mantle is 5 gram per centimeter cube, and the radius of the core is 3480, that is the realistic scenario, then it basically matches with the real value of the earth, that is 0.33. So basically we can say that after having these cases, it indicates that the dense core is there at the center of the earth, which basically further indicates that there is a material which is much denser inside the body of the earth, that means near to the center of the earth. Now let's look at the variation of the density with depth relating the seismic velocities, and we can consider a region of uniform material and see how the density increases with depth as the material is self-compressed by its own weight. So we are going to consider the gradient of the hydrostatic pressure, that is PR, pressure as a function of radius, that will be equal to dP by dr, that is the gradient of the hydrostatic pressure, that will be is the negative of the acceleration due to gravity times the density rho. This negative sign is there because the pressure is increasing with depth, and since g is equal to gm upon r square, that then we can incorporate this particular value into this particular expression, then we will get dP by dr is equal to rho gm by r square. Then if we consider the regular formula for the density, that is mass per unit volume, and the elemental dilatation, that is dv by d, that is d theta is equal to dv by v, then we can possibly write the value of d rho after taking the differential of this, that will be d rho is equal to minus m by v square dv, that will be equal to minus rho d theta. So this basically gives you the d rho by d theta is equal to minus rho. Then if we express the bulk modulus K as equal to negative of the differential pressure by dilatation, then it will be equal to minus dP by d rho and d rho by d theta, where we are multiplying the numerator and the denominator by d rho, that will be equal to rho dp by d rho, because minus dp by d rho is equal to rho, that we have seen over here. So uh, that will be equal to rho dp by d rho. Sorry, this should be d theta. So dp minus dp by d theta is equal to rho, and that will further give you the value of rho dp by d rho. Combining this with the pressure in the pressure derivative in the equation 1, then what we will get, dp by dr is equal to minus t rho by dp. So dp is multiplied on the numerator and the denominator both, and then divided by dr, that will be equal to rho square gm by kr square. Then in order to have it to get linked with the seismic velocities, we are going to define a parameter phi, and the bulk sound speed as phi to the power 1 by 2. Then what we will get, phi is equal to alpha square minus 4 by 3 beta square, that will further be equal to k by rho. And when we will write that and incorporate it into this particular equation, we will get this equation here, which basically relates the velocity structure to the derivative of the density with the radius, and then it will become d rho r by dr is equal to minus d rho as a function of radius g mass as a function of radius by phi r square is equal to rho r gr by phi r. And this particular equation is famously known as Adams-Williamson equation. As I said, it can relate the velocity structure to the derivative of the density with radius. So derivative of the density with radius is this term, and it is relating the velocity structure, that is in terms of phi r, that is the bulk sound speed or seismic parameter. And this Adam-Williamson equation is considered to be insufficient, because we are considering the case where the density is increasing with depth only because of the self compression, but there is a contribution which we cannot neglect due to the mineral phase changes. As you go deeper, the phase of the minerals are keep on changing, that will also contribute to the increment in the density with depth apart from self compression. So if you look at this particular figure here, this is for the uniform earth for the value of c by ma square for the core. So for the core, c by ma square we got was 0.4 in case of uniform density, and in case all the mass is concentrated near to the surface, then its value what we got was 0.67, and as you increase the density with depth, then its value will keep on reducing. And finally, when you have most of the density, or you can say the density is more near to the higher depth, then you may basically reach to the more realistic scenario. But let's see what is written here. Figure shows the c upon ma square value calculated for the core as a function of the assumed density at the top of the mantle, which is the initial density for the Adams-Williamson equation. And then if we consider the near surface density as 3.3 gram per centimeter cube, that is the average density of the near surface rocks, this will basically give you c upon ma square 0.4 that we have seen already, which implying that density decreases with depth. So this, if we consider that the density is decreasing with depth in the core, then it basically is not a true consideration, because we know that in the inner core, the inner core is solid and the density is larger than the liquid outer core. So in order to have much better or much realistic considerations for the Adams-Williamson equation, there was a scientist with the name of F. Birch who showed that at least one of the two assumptions underlying the method was inappropriate. And in those particular methods, we considered the temperature increases with depth along an adiabatic gradient, that is also known as adiabat, and which is also not always true. And in fact, the temperature gradient in the mantle is thought to exceed the adiabatic gradient because super adiabatic gradient is required for the thermal convection expected in the mantle. So we are going to consider the super adiabatic gradient, and that we will incorporate into the Adams equation, and after the incorporation we will get this expression for the gradient of the density with respect to the radius, that is equal to negative of rho g by phi plus g tau alpha, where alpha is the coefficient of the thermal expansion and tau is the portion of the temperature gradient exceeding the adiabatic gradient. And after you apply this super adiabatic correction for the higher temperature in the mantle, then this higher temperature basically lowers the calculated mantle density and increase the value of the C upon MA square, which basically make our case even worse. So we need to correct this for basically the homogeneous material that is lying at the depth of more than 1000 kilometers, and until the upper mantle the material is kind of inhomogeneous, and that can be identified using the function this that was given by F. Birch. So when we consider this particular function onto the y-axis of this graph, and there we have the depth, when we plot the points, then you can see at around 1000 kilometer depth, the below which the material is having the homogeneous nature, and at the shallower depth up to 1000 kilometers it is having the inhomogeneity. And below 1000 kilometer the mantle behaves as a homogeneous material, while at shallower depth it does not. This is because the mineral phase transition expected at the depth of 410 kilometer and 660 kilometer discontinuities that involves denser atomic packings, and therefore transitions to higher densities than predicted by Adams-Williamson equation. And as a result, the density model of the Earth include rapid changes at the transition zone. So this is the preliminary reference Earth model of P wave velocity, S wave velocity, and the density. And this is the P wave velocity here, which is represented by a solid black line, and there is this dash line which is representing the S wave velocity, and this dash dot line is representing the density. And you can see there is this transition zone, and up to around 1000 kilometer if you see, then in this area the density variations are basically larger than the smooth variations in the lower mantle or the outer core and the inner core. So this is what it is written. As a result, density model of the Earth include rapid changes in the transition zone, which is in the upper mantle at 410 kilometer and 660 kilometer discontinuities, and within the lower mantle, outer core and the inner core density increases smoothly with depth according to Adams-Williamson equation. Now let's have a look at the pressure variations within the Earth. So a density profile is basically used to compute a pressure profile, and thus use the result of experiments showing which mineral phase exists at a particular pressure. So the pressure value can be written as the negative of integral from 0 to r gr rho r dr, where gr is the acceleration due to gravity variations with respect to the radius, and the density with respect to the radius is given. There are a few points that we must remember, and these graphs are also given, which shows the density variations with respect to depth, the gravity variations with respect to depth, pressure variation with respect to depth, and the mass variations with respect to depth. So the gravity, the average value of the gravity is 9.8 per meter per second square at the Earth's surface, and is basically 0 at the Earth's center. Gravity, if you look at this graph, it increases slightly across the mantle like this, and then it reaching up to a maximum value of 10.7 meter per second square at the core mantle boundary. So this is the core mantle boundary, and because of the high density of the core and the relative to the mantle, it's basically peak at this particular core mantle boundary. And if you go further depth, then its value of the gravity decreases towards the core and reach to zero. The core has only 16% of the Earth's volume, but it has almost one third of the mass. So, for the summary of the today's lecture, the ratio of moment of inertia to the mass gives a scalar that depends on the density distribution. Adam-Williamson equation relating the velocity structure to the derivative of density with radius can be given by this, which is d rho r by dr is equal to negative of rho as a function of r, gravitational constant, and mass as a function of radius divided by seismic parameter phi r and r square, and that is further equal to rho r gr by phi r. The drawback of Adam-Williamson equation is that it does not take the account of changes in mineral phase with depth. And the modified form of Adamson-Williamson equation, which includes the super adiabatic gradient, is this: d rho by dr is equal to negative of rho g by phi plus g tau alpha, where alpha is the coefficient of thermal expansion and tau is the portion of the temperature gradient exceeding the adiabatic gradient. Then F. Birch introduces the inhomogeneity in the earth that can be basically identified with this function, and pressure inside the earth can be computed by this integral that relates the pressure with the density variation and the acceleration due to gravity, that is equal to negative of integral 0 to r gr rho r dr. And this is all for today's lecture. We are going to meet in the second lecture of module 8, and these are the references, and thank you so much. Bye bye.